As was mentioned, I'm from the Argonne Leadership Computing Facility, and we've been working for the last several years to stand up Exascale system Aurora, and we're getting close to the finish line there. This talk was aimed at sort of giving folks who are interested, a little bit of background on the project, what we do at the Leadership Computing Facility, and how the work has progressed and where we are sort of, on the path to Exascale, in our center. So it's not going to be a deeply technical talk on one specific topic. I'm not going to go deeply into the architecture or into an individual application, but I will kind of give you an overview of both the system, hardware, the software, and some of the applications that folks have been working to prepare to run on the system when it's ready. And we have some performance data and some information on the approaches that they've used to get their codes working on our testbed systems, and so you can get a sense of where things are today and what tracks the applications have taken and what results they've gotten so far. But first, before I get on to Aurora, I do want to give folks who are not familiar with the Argonne Leadership Computing Facility, or the ALCF, a little background on what it is and where it is that Aurora will be living. So the ALCF is one of two Department of Energy leadership computing facilities that provide large-scale HPC systems to the scientific community. So us and our sister facility at Oak Ridge, provide access to Aurora at our system and Frontier at the Oak Ridge system, which are both Exascale Center, which are both Exascale platforms to basically the worldwide scientific community. So there's a competitive proposal process that any researcher around the world can apply to, and those proposals get vetted and the better ones selected and awarded, and so anybody doing what we call open science research, so stuff that will be published, it's non-proprietary, is welcome to apply. And then if they're given an award, they'll get a significant amount of time on these systems in order to do typically things that are not feasible on other platforms, anywhere else in the world. Our intent in the goal for this work is that, all those results are published or otherwise made publicly available to the scientific community. So the ALCF, in addition to, providing the hardware, we also have a large staff of experts who have a lot of experience working with HPC systems and software. And so, we're able to provide help to the users to make sure that they're getting the best results from our systems. And we've been doing this for a while. The ALCF has been in place for a little over 15 years now. What we've seen over particularly the last decade is there's been this, slow but steady shift from just solving PDEs and doing what we would call traditional simulation work to newer approaches to solving problems. And so these involve analyzing large data sets that come from scientific instruments, like telescopes, things like that, and also now more recently applying machine learning techniques to drive the science forward. And so with Aurora, we're trying to provide a leadership class resource to solve all those dimensions well, and enable people to solve problems in any of these forms and with any approach that they prefer or find most effective. So the scope is a little broader than what we've done in the past with these machines. Both the hardware and the software have to sort of encompass a broader set of approaches to doing science today. So as I mentioned, the ALCF has been around for over 15 years, going on 20 now. We've fielded a variety of machines over the years, which have generally been at or near the top of the top 500 list. So our first big machine was in 2007 with Intrepid. That was a Blue Gene P system. The follow-on to that was Mira, which was a few years later, which was a Blue Gene Q system. That was a 10 petaflop system, which at the time I think was number 2 or 3 in the top 500. Today that seems small, but at the time it was a big machine. Our most recent machine is Polaris, and you'll notice that it's not dramatically bigger than Mira. It's only about 4 times larger, and typically we're trying to get 10 times larger or something like that with each iteration. And the reason for that is that it's become increasingly complex, and the landscape for large-scale HPC has shifted, and so that's involved some some rethinking on our end as to how to approach that, and how to best field a platform that's going to be most useful to the scientific community. And what you can see is the change in the HPC landscape, I think, is well represented by what the DOE has been doing recently. So over the last 5 years, these are the machines that the Department of Energy in the US has either contracted for or has deployed and has in use at their facilities. And you'll notice that, you know, virtually all of them these days are accelerated platforms. You know, so the earlier ones were all primarily NVIDIA accelerated machines, and now today we're starting to see, you know, AMD and Intel accelerated machines join the group. And so with one exception, which is the Crossroads system, these are all GPU accelerated platforms. And so really at large scale, you know, for large scale computational resources, what we're seeing is that, you know, CPU only systems are becoming the exception, you know, rather than the rule, which was a large change from, you know, 10 years ago where they were sort of a novelty and a unique platform. Now they're starting to become the mainstream, at least for large scale HPC. And the reason for that is driven by a number of factors. It is getting, you know, harder to follow Moore's law these days. You know, if you talk to different silicon vendors, some of them say, you know, that they're, you know, following Moore's law more closely than others. But I think everyone will agree that, you know, it's not as easy and it's not happening. The increase in transistor density is not, you know, happening quite on the same cadence maybe that it was in the past, doubling, you know, every 2 years. And for large scale systems, another important factor is the end of what they call Dennard scaling, which is where the flops per watt required, the watts per flop required was decreasing, you know, as the transistor density increased. So we're not seeing that decrease in the same way that we were before, which means that these systems are drawing increasingly more power. So it used to be that a large scale, you know, sort of top 10 in the world machine would draw, you know, maybe 1 to 3 megawatts of power. And now today, these large scale systems are drawing in the tens of megawatts, up to like, you know, 40, 50 megawatts of electricity to operate. And so that is a significant cost. You know, for us at Argonne, I think as a ballpark number, a megawatt of electricity for a year costs $1 million. So if you have a, you know, 20, 30, $40 million or megawatt machine on the floor, you're looking at, you know, tens of millions of dollars just in electricity cost alone. So, you know, optimizing that puts a major constraint on what we can do, and optimizing that's an important element that we're looking at in our future systems. In addition, the cost of new process technology is rising, which means transistors are starting to get more expensive rather than less expensive. So all these, you know, factors, you know, have combined to sort of create opportunities for new architectures, you know, so it's not just, you know, iterate on the CPU, add a few more cores, bump up the clock speed, and that's your new generation of system anymore. It's, you know, there's a lot more innovation going on, and we're seeing sort of, you know, more unique hardware that is more optimized and better able to deliver a balance of, you know, cost, power, and performance. But that said, you know, HPC systems have generally only been cost effective when they're leveraging commodity technologies. So it's just cost prohibitive these days to develop a sort of one-off architecture only for HPC. And so that's where the GPUs come in. So, you know, we're leveraging all of the investment that's gone in for the gaming space, but that actually ends up being well suited for the kind of HPC workloads that we also want to run. And these kind of GPU-based architectures are delivering better performance per dollar and per watt than a CPU-only architecture would for our systems. So that's how we are sort of moving into this GPU space, primarily for the larger scale systems. But however, you know, with new hardware, there also comes a host of challenges in the software and the application domains. You know, so we need a new set of software, and the applications have to adapt for that. So now I want to talk about a little bit about, give you a little background on Aurora specifically. So I think, you know, obviously at this, you know, based on what I said, you'd expect Aurora to be a GPU-based system. And we are doing that with Intel's new data center GPUs, so the Intel Max data center GPU Max Series. This is something that was previously known as the Ponte Vecchio GPU. So Aurora will be a large system. We're targeting over 2 exaflops of peak double precision performance. So that should put it at or near the top of the top 500 list. So we anticipate it being, if not the largest, one of the largest systems in the world in terms of computing power. The system will have over 10,000 nodes. Each node will have 6 GPUs and 2 CPUs. So as a result, we're looking at over 60,000 GPUs on the system and 20,000 CPUs. Now, to make a supercomputer really effective for the kind of workloads that people want to do. It's not sufficient just to have a lot of raw computing power. This all has to be tied together with a fast and efficient network. And so for the network, we are using HPE's Slingshot 11 network to tie all the nodes together. And I'll talk about that a little bit more later. So in addition to the computing power, Aurora will have over 20 petabytes of memory. So this may be the largest amount of memory you'll find on any machine in this time frame, and that memory will be split pretty much evenly between regular traditional DDR5 memory and HBM2E high bandwidth fast memory, HBM2E memory. And this memory the HBM2E will be both on the CPU and on the GPUs. So the CPU part is sort of novel. That's not something that's been put into production in many places yet. In the network side, we'll have over 2 petabytes of injection bandwidth into the Slingshot network, and about 0.7 petabytes of bisection bandwidth. So this is sort of the narrowest point of the network. So that's the amount of network that you could exchange from one half of the machine, or data you could exchange from one half of the machine to the other. But we expect this to be a very high performance network for this system. And the file system will be based on Intel's new Deus architecture. So the file system will have over 230 petabytes of storage, and will have a read-write bandwidth of around 31 terabytes per second, which is quite large. So while the system will have a lot of flops, like I said, I think we will also expect to see it have possibly the most memory and the highest, the most memory network bandwidth, along with the best storage performance of any machine, put on the floor in this time frame. And this is really what we want, is a balanced architecture where the machine is not just a flop-heavy platform that is bottlenecked on other things, but is able to deliver performance across this wider range of workloads that we anticipate people doing, both simulation, data analysis, and machine learning. So if you look at the node, I think this is a pretty typical design for what we're seeing in GPU accelerated systems these days. So the node board, which is sort of in the center, what you'll see is those sort of 6 blue, silver things with the blue little rectangles next to them are the GPUs. So there's 6 GPUs, the PVC or Data Center Max GPUs. Each of them have 128 gigabytes of HBM2E memory. And the GPUs will be connected in an all-to-all fashion with Intel's Xe Link. So there's you can rapidly transfer data back and forth between the different GPUs on a node. In addition to the GPUs, there will be 2 of the Sapphire Rapids or Xeon Max Series CPUs. Each of those will have 512 gigabytes of DDR memory and 64 gigabytes of the HBM2E memory on the CPU die. So the CPU will have significantly higher bandwidth that it can achieve from that 64 gigabytes of HBM memory. The GPUs and the CPUs will be connected with PCIe Gen 5 links. And we also have 8 of the Slingshot network adapters or NICs per node. And these will be able to move the data directly back and forth between the GPU and the network without having to first buffer it in the CPU before sending it across the network, which helps to lower the latency and increase the bandwidth for network operations. So quickly, I just want to talk about the Sapphire Rapids. So Sapphire Rapids is the latest generation of Intel's Xeon CPUs, and it is the first in the Xeon line to include the high bandwidth memory on the CPU, which will help improve performance for memory bandwidth bound applications that are running on the CPU. So in some sense, this is a novel CPU, but it's also, if folks are familiar with Intel's past products, it's an evolution in some ways of the Knights Landing processor that Intel had and that we had on the Argonne Theta system that we're still using today. So the number of cores is a little bit different, and it's a different type of high bandwidth memory. But this is an architecture that we've had some familiarity with from using on our previous platforms, and also some that we've really had some good success with. So we're really looking forward to having the faster high bandwidth memory on the CPU to help drive those workloads that are bound by memory, which is quite a few workloads in the HPC space that are running on the CPU side. So, you know, the big thing that's really new for Aurora is the GPU, so the Ponte Vecchio or Intel Data Center Max GPU. So this is, you know, the first large scale, you know, data center oriented GPU that Intel will be putting out that is, you know, competing with the other ones from NVIDIA and AMD that have been used on other platforms. So I'm not going to go into detail on the architecture. I'll talk a little bit about it, but that's a much larger talk and one that I think Intel has probably better resources online today, you know, from other talks that are out there than I'm able to cover in this talk. But I will say a few things about it. I mean, first I will say that it is a very complex chip. I think Intel's, at least some Intel folks I've heard describe it as the most complex chip they've ever made. You know, this chip itself has on it over 100 billion transistors. So it's quite large. If you see one in person, it's a very large package. You know, basically, you know, you need, you know, really covers your entire hand when you're holding it. And one of the unique things and what we're seeing a lot of, you know, evolution towards is to having multiple chiplets on a single die. So in this case, Ponte Vecchio is assembled from a bunch of little, you know, different pieces of silicon. And Intel's indicated there's, you know, 47 tiles or chiplets that go into making up the PVC GPU, which is quite a lot. I mean, it wasn't too long ago that, you know, all of these things were basically one monolithic piece of silicon. And today they're, you know, really optimizing this by creating a lot of different components on different processes. So you don't need the latest and greatest, you know, smallest transistors for every component of a GPU, right, or a CPU. You really need that where it's really useful to have that high transistor density and those fast and efficient transistors. But there's other parts where you don't need that, and so you're really spending money and power on things, you know, where you may not need it if you just went with one process. So in this case, Intel's used, you know, 5 different processes to compose, you know, to build these tiles, and then composed all these tiles into a single socket that gives you the Ponte Vecchio GPU. And so briefly, this is sort of a very, very high level, very brief overview of the Max GPU. But the core of it is the XE, what Intel calls the XE cores. So these are the basic building blocks where the computational gets done. And so this is what you see in the upper left corner there. So this is sort of the fundamental building block for the GPU, and it consists of 8 vector engines and 8 matrix engines, along with a 512 kilobyte L1 cache. That can be configured as either a traditional cache or sort of, you know, program managed shared local memory. So 16 of these XE cores are grouped together into what's called a slice. This sort of bundles these together, those core XE cores together into the slice, and then 4 slices are combined along with a large L2 cache and 4 HBM2E memory controllers to form what Intel calls a stack, or in the past they called a tile. We typically still call it a tile. And that's the sort of major component of the GPU. And so one or more of these stacks or tiles can then be combined on a die to give you the GPU. So in the case of the Ponte Vecchio that we're using, there's 2 tiles or 2 stacks on the die that compose each GPU. So the other major component of making these machines work is the network. I think at present, all of the large-scale US-based machines are using HPE's Cray Slingshot interconnect. So that's sort of the latest and greatest evolution of their previous network technologies that were found on earlier machines. And so this feature has a number of, you know, things that we've seen on past high performance networks that have been, you know, improved and, you know, evolved, along with some newer components that we hope to see, you know, significantly impact and improve the network performance on these machines, because it is a critical component of getting large scale applications to work. So one of the main components that I think novel and potentially highly impactful in Slingshot is what they call multi-level congestion management. So this really is making the network smart enough that it can look at the traffic that's flowing across the network and try to minimize the congestion that occurs for multiple applications, both trying to communicate at the same time. So the idea here is to drive down the latency of a given network operation. So if you do an MPI send operation, or a direct memory put or get. What you'll see sometimes on a congestion network is that a lot of those will go pretty fast, but some of those will go 10 to 20 times slower than the fastest ones. And this is because, just like when you're driving in traffic, in a congested city, you get stuck in traffic and it takes much longer, for you to arrive or for that data to arrive. And so in this case, what the network is trying to do is route traffic and manage traffic in a way that optimizes the flow across the network and make sure that no one application is suffering a lot of delays in their delivery of their network packets, such that it impacts the performance of their application. So the idea here is to give faster or more consistent performance across the network when there are multiple applications competing for the network resources. So that's something new in these networks that I don't think we've really seen before, and we're looking forward to seeing operate at these large scales. Another new feature is aggressive adaptive routing. So that lets the network take multiple routes between any two endpoints. So if you're sending from one node to another and the path that you would normally take has a lot of other traffic on it, the network is smart enough to see that traffic and route your packets around that traffic, through a different set of switches, and then arriving at the same point. And that way, also helping to mitigate the delays that you might see going through the system. Another feature is the QoS, or quality of service classes, that the network implements. And so that lets us put different network traffic in different categories and decide which ones should be given priority. So if you're doing a sensitive all reduce operation, right, so you're doing an MPI operation where you want to minimize the latency, that might be those packets may be given the highest priority, so they can basically cut the line when they get to the switch and go in front of everybody else, because delaying those will significantly impact the performance of your application. Whereas if you're doing a lot of writes to a file system for a checkpoint, and you don't necessarily care that much, that it'd be perfectly optimized, right? You can suffer a little bit of latency there on that operation. That IO traffic could be put in a lower QoS class and deprioritized so that it doesn't block the high priority packets for your reduction operations, let's say. So there's a number of features here that we're looking forward to seeing in operation on a machine, because the network makes a crucial part of these platforms. And for those who aren't familiar with the Dragonfly topology, and you'll see this across pretty much all of the Slingshot networks that are in operation today, the basic idea behind a Dragonfly is that the nodes are organized into groups. And so a group in our case is a rack that contains 64 of our nodes. And those are connected within the group, to a number of switches that let each node communicate directly with any other node in one hop. And so this is an all-to-all communication arrangement within a group. So you have very rich, low latency, direct connectivity within a group. And then on Aurora, we're going to have 175 of these groups. So there'll be 166 compute groups that have the over 10,000 compute nodes in them, plus a number of IO and service groups. And these groups then have all-to-all links between each one of them, but they're not as high bandwidth, or there's not as many links. So the amount of bandwidth between any two groups is less than what you see within a group itself. So this is sort of a hierarchical arrangement. And the idea is that if you're running a job and you have multiple group nodes, MPI processes within a group, they can communicate very quickly, and then in many cases there's not as much information that needs to go out of the group between other groups, so that you don't need as much bandwidth there. And they can also use the multiple links and use indirect routing to take a hop between, instead of going directly between two groups, they can take an indirect route and hop to another group and then back to the target group. So there's a lot of paths that let data flow between any two groups. So that's just an overview of Slingshot. The other dimension of the system I mentioned was the file system. So on Aurora, we're going to have a fairly novel file system. So this is a new architecture that Intel has developed called Deus, which stands for Distributed Asynchronous Object Store. And this will be our main high performance file system. In addition to that, we'll also have our existing ALCF Luster file systems called Eagle and Grand connected to the machine. So any data people have previously saved on our systems will be available on Aurora too. So as I mentioned, the Deus file system will have a usable capacity of over 230 petabytes. And it will be very, very high performance. We'll have over 31 terabytes of read-write performance. So just for comparison, our existing file systems have 650 gigabytes of performance. So we're looking at over 50 times faster read and write performance on the Deus file system on Aurora than what we're seeing today on our existing file system. So this should be a big boost for anybody that's processing large data sets. In addition, so Deus is sort of a novel architecture for the underlying components of the file system, and so it will provide new storage APIs that will enable applications that have IO needs to do new things that they weren't previously able to do on POSIX file systems. But that said, it will look very familiar at the top level to anybody that's used a traditional file system. So it will support all of the previously used IO models, so things like POSIX, MPIO, HDF5 will all work seamlessly and won't look any different to anybody that's used to using those. So this will be an interesting both addition to Aurora, both in terms of the raw performance and the new capabilities that it delivers. Okay, so where are we with Aurora today? So today we are in the process of bringing up Aurora on the Argonne data center. This slide, we have a few pictures of the racks in the machine room as more or less as they look today. So you'll see, each of the individual racks, all the electricity is in the sort of silver boxes near the top of the ceiling. So those are all the electrical connections that come down into the racks. The water generally comes up through the floor, and the blue and red coils that you're seeing, or the loops that you're seeing sticking out of the racks, those are all piping. So that's water that's flowing through there. So the blue is cold water and the red is hot water. So the whole system's water cooled. So every individual component on the machine is water cooled. And you can see that in the picture on the left. You can see those white sort of tubes going between the GPUs and going to the CPU. So they're all carrying water that go into a heat exchanger that's directly connected to the GPU. So the whole machine is water cooled. So there's quite a lot of water flowing through the system, and that's what you're seeing a lot of in these pictures. But we have all the hardware on the floor today. And right now we're in the process of bringing the machine up. And as you can imagine, with 60,000 GPUs, 20,000 CPUs, and I think 80,000 network endpoints, not to mention several thousand switches and probably tens of thousands of network links. Not all these things are going to work perfectly out of the box. So there's a period where we have to go through and iron out the kinks, identify anything that's not working or configured correctly, straighten that out, and try to get that all working in concert so that it's usable as a system, as a whole. So we're in the process of doing that, and our hope is that we can start making the system available to early users this fall. And this is a very simplified snapshot of the status of the applications that we plan on running on Aurora once it's fully installed. And I'll talk about this slide in more detail a little later on, but the main gist is we have over 40 applications that we've been working with the HPC community over the last couple of years to get ready to run on Aurora. And the ones that are marked in coded in or tagged in green are in what we consider to be good shape and pretty much ready to run, at least at the single node level. So anything in green is is working with the darker green ones running sort of in a more optimized fashion than the lighter green ones, and the ones that are in yellow and orange are ones that are still working through elements of their porting process or addressing issues that they've encountered. So they're not quite fully there yet, but they're getting there. And so what we're seeing is over half of our applications are sort of in this green state, which means that they are, they could run if Aurora was there on the floor today, which is really, what we want to see. We want to have these applications ready to go when the machine's on the floor. And I'll talk about this a little bit more later on. So there's still work to do before we can, put Aurora into production and make it available to the wider HPC community. So we have to complete the initial system bring up. Then we have to verify that everything is working, and we do that through what we call an acceptance test, where we run a whole series of tests and validate that the system is working as expected, and then we accept the system and put it into production Argonne. Then we're going to run a number of what we call our early science applications, along with a number of applications from the DOE Exascale Computing Project, and run them across the machine at scale. And so in many cases, this would be using half or more of the machine, on a given run to get, very large scale scientific results out of it. And then finally, we'll put the system into production. But at this point, we can say that a lot of the major risks that, we worry about, have been mitigated. So, we have all the hardware, it's on the floor, it's, in most cases, most of it's working as expected. The Intel initial performance results on the GPUs are looking good, and the software stack is really coming together and maturing at a very good pace. So we're pretty happy with where things are today, though, like I said, there's still quite a bit that we have remaining to do. I do want to mention briefly, we're just getting the Aurora hardware today. So prior to that, we've been working to get applications ready for years, and it's a major risk, running on new hardware. So what we've done is we've used a series of test beds that Intel's been able to provide us to work on the applications over the last several years. And so while the high performance data center GPUs are something that is new to Intel, Intel GPUs in general are not. Intel's been building and shipping millions of GPUs for over a decade. However, these have been integrated with their CPUs. So if you look in the upper right, you'll see a picture. I think this is from a Tiger Lake CPU, and the area kind of outlined in red is the silicon devoted to the GPU on that chip, which is roughly 30 to 40% of the chip. So it's not a small fraction of the chip itself. So this is something Intel's been doing for a while, and really what we're seeing in these new GPUs is that Intel's leveraged and evolved their existing GPU expertise into this new range of products. And this will span a broader range of applications from, what they've done in the past, which is integrated GPUs to gaming GPUs to data center GPUs. And so this has, really lowered the risk for our project, given that, the foundation that this is being built on. It's been around for a while. So I won't say a whole lot about this, but as I said, we went through a number of test beds. So starting back in 2019, we were running on what we called the Iris test bed, which was just a Gen 9 integrated GPU. So it's very small, very low performance, but the nice thing was it let us test all the software. And so we could start running HPC applications on these sort of embedded GPUs, and they ran just fine. I mean, they didn't run super fast, but we were able to sort of identify issues in the software stack and say, hey, my code's having a problem with this. Let's work on fixing that. And so that gave us a big jump start on getting these issues resolved. And over this time, the last several years, we've gone through a succession of these test beds until in 2022, we got our first test bed with the Data Center Max GPU. That one was called Florentia. It was a little different from what we're seeing on Aurora. It only had 4 GPUs, but it was a very useful platform for us. And nowadays we're running on just a couple of cabinets of the Aurora hardware that we've called, carved out and called Sunspot. And so that's our test and development center, our system for Aurora, and that's where we're doing all of our work today while Aurora is being brought up. Okay, so I said, with the new hardware, there comes a whole host of things that have to be done on the software side. So I want to quickly walk through some of the work that's been done and some of the changes that have occurred in the software environment to enable applications, to run on this new hardware. So one of the challenges with new hardware is this new software, and Intel's solution is the one API. Software environment. And so unfortunately, instead of adopting sort of a proprietary approach for their hardware, Intel's sort of done the opposite and gone, with a much more open standardized approach, and made a number of their, important critical software components for their GPU software stack, for the Aurora software stack, open source. So the main components of one API are the DPC++ compiler, which is Intel's implementation of the SYCL programming model, and I'll talk about that a little more in a couple slides, along with a number of library interfaces. And Intel's promoted both the DPC++ compiler, the SYCL which is an existing standard, and their library interfaces as sort of an open standard for the community. They also have a hardware abstraction layer called level 0, and so that's the runtime that sort of everything sits on top of to run on their GPUs. You'll often hear one API mentioned as sort of a software development kit, and so that really encompasses sort of a broader set of tools and components than just the one API standard components. So this includes things like Intel's, existing C and C++ compilers, along with the new Fortran compiler for the GPUs, their Python compilers and runtimes, along with an MPI library and tools such as vTune, and learning frameworks such as PyTorch and TensorFlow. So the nice thing is, if you've run on Intel hardware before, right, even just using a CPU, a lot of these things are going to look very familiar to you, and make it easier to move your code over to the GPU. And so on Aurora, in addition to supporting the DPC++ SYCL programming environment, we've also chosen to, make sure that we can support a number of other programming models that are being used commonly to run on GPUs today. So including the ones that come from the Intel One API software stack, which includes SYCL, OpenMP, and OpenCL. Aurora will also provide Cocos and Raja, which are sort of DOE-led portable programming models. And we won't, however, be able to provide CUDA, as CUDA is proprietary. However, as an alternative to CUDA, there is HIP, which has been developed by AMD. And we've been working with Intel and AMD on making a version of HIP available on Aurora. So this provides a fairly simple porting path for applications that want to continue to use something that's largely related to CUDA. So if they have an existing CUDA implementation, the path to running on HIP is relatively straightforward. And you'll see there's a pie chart in the lower right, and what you'll see is this sort of outlines who's using what, how many applications are using the different programming models, and you can kind of see, with, even without looking through the chart in detail, that there isn't sort of really one dominant programming model these days. So the programming model space for running on GPUs is fairly diverse at the moment, and so that means we have to be able to support these multiple programming models for our system. I did mention DPC++ is Intel's SYCL compiler. For those who aren't familiar with SYCL, it is a newer programming model for heterogeneous systems. It's actually been around for a while. I think it came out, the initial draft of the spec came out in 2014. But I think it's really started to gain a lot more traction in the last couple of years. So the latest SYCL standard is SYCL 2020. It was released back in 2021. And so SYCL in a nutshell is really a C++ oriented way of offloading code to the GPU that is sort of derived from the lessons learned from OpenCL, and it adapts and applies those to C++. And I think provides a very natural programming model for C++ developers. DPC++ is Intel's implementation of SYCL. So it really is just largely a SYCL compiler with a few extensions that Intel generally brings back to the community and says, hey, we found these to be useful. So you should consider adding them to the SYCL standard. And in many cases, that has happened. So in addition to Intel's DPC++ implementation, there's also a number of other SYCL compilers out there that people can use. One of the major ones is from CodePlay. And this is something that runs not just on Intel GPUs, but on a variety of other GPUs. So it runs on AMD GPUs and NVIDIA GPUs. And I'll show you at least, some results that we have, at least for one application that's been able to successfully run across all three GPU platforms using SYCL and get good performance. So I think most people are probably familiar with OpenMP. It's certainly been around for, several decades now. Traditionally, it was used for, multi-threaded, multi-core programming for CPUs. But, over the last couple of years since the, version 4.5 of the spec, they've also included pragmas that allow you to offload to GPUs. And so one of the nice things about OpenMP is that it works with both C++ and Fortran. So if you're a Fortran developer, this may be your sort of only real option for native offload in using Fortran. And multiple vendors have announced support for OpenMP offload. So this has the potential to be a fairly portable programming model too. And I do want to quickly mention Fortran. So Intel has had a long history with Fortran. They have a very strong Fortran development team, and we're seeing the results of that on the on the Aurora system. Intel has a newer Fortran compiler for their GPUs that implements OpenMP offload, and that's been maturing quite rapidly. And we were able to run, a number of our Fortran OpenMP based codes along with C codes using OpenMP very successfully on the Aurora hardware. So now I want to take, my last section of the talk. I want to take a few more minutes to, kind of walk through where we are with the results, of applications running on the, the Aurora hardware. So in this case, it was on our Sunspot testbed system, but that is, the Aurora nodes, just a handful of them set aside for application use. So the applications for Aurora are coming from primarily two programs. One is the Argonne Organized Early Science Program, which has 19 projects. 9 of them are sort of simulation oriented, so traditional sort of PDE type solvers. 5 are learning oriented, so they're using newer machine learning techniques for their problems. And 5 are more data intensive, where they plan on doing analysis on large data sets. In addition to that, we are working with 15 of the DOE Exascale Computing application projects to get their codes ready to run on Aurora too. So several of these projects contain multiple codes. So all in all, we're basically working with about 40, 45 codes to get them ready for Aurora so that they're ready to run on the machine when the machine is available. So a handful of these codes are part of workflows, and they're not critical, they're not performance critical. So they may just run on the CPU, but virtually all the others, so 40 some odd codes are running today or will be running on the GPU. And I do want to say that many people have been involved in this effort over the years. So we have at least 60 people at Argonne and Intel that have been working with the project teams to make this happen. And there are more than 100 people outside of Argonne and Intel at various universities and laboratories that have also been working on this and contributing. So it's been quite a large effort and a large group of people, but this is pretty typical of what's required to prepare applications for this sort of next generation platforms. And what we've done is we've paid a lot of attention to the progress that these groups have made over the years. And so starting back in 2020, we started surveying them and kind of tracking how they were doing in multiple dimensions in their path to getting their applications ready for Aurora. And we saw this in sort of about 5 critical dimensions that they all need to be successful in order to get their applications ready to run. So the first is, on this scale hardware, most of these guys are trying to do new things, right? Things that have never been done before. And in many cases, that means, implementing new features and algorithms in their code. And so that's what we call their science implementation. So, we've asked them, is your science there? Is your code capable of doing the science that you want to do when the system's available? And so over the years, we've seen that, most of them have said, yeah, it's either partially or fully, implemented. And so if you go back to the orange bar there, back in Q4 of 2020, about 27 of our codes said, yeah, we have our science fully implemented. And that's, kind of crept up incrementally over the years, so that today, 41 of our applications, which is the blue bar on the right of the graph that's on the left side of the chart, have said, yeah, we have our science fully implemented. We're ready to, do the kind of simulations or analysis that we want to do. And that's basically almost all of our codes. There's a handful that are still tweaking things. We have 4 that say that they're partially ready there, but I think in most cases, they're pretty much ready to go. They're just, playing around with some of the details. And another dimension is, in the science implementation case, we're just asking them, is the code there? Not can it run on Aurora, but can it run anywhere? So maybe it's a CPU only implementation. So if they have their science in a CPU only implementation, the next step is to port it to run on Aurora, which generally means running on the GPU. So we asked them, is your code ported to an Aurora programming model? And here you can see that, we had people say, no, not at all. And at this point, we're down to 0 of those. Many of them said, yeah, we're partially ported. And when we started this work, about half of them were only partially ported. Today, we're down to about 5 that are still sort of work in progress. And we've seen a nice uptick in the numbers, starting with, just 9 that said, yeah, we're fully ported, up to, much larger number. That's almost all of our applications today. They're saying, yeah, we're fully ported to an Aurora programming model. And so this, at this point, 2/3 of our applications are, at least fully ported to run on the machine. This is the slide that I showed you before. So the next dimension is, once your science is implemented and you're ported, can you actually run, right? Can you run? And we start with the question, can you run on a single GPU? Can you run on a single node? And can you run with performance, right? And so that's what's sort of reflected here is the status of applications and their ability to run and run with performance. So the ones in dark green are ones that we consider, running with good performance on a single node of our testbed systems. And so about half of our applications are at that point, which I think is pretty good for where, the stage of the game. It always takes a long time to iron out all the issues and really optimize the performance. But we're pretty happy with where we are today. But that doesn't, that being said, there's a number that are, not quite there yet, and we're continuing to work with those. And in most cases, they're able to run, but the performance is not quite where we want it to be, and we're continuing to work on that. Or, they have some issues in the programming environment. In many cases, they have workarounds in place for things that, maybe the compiler's not handling optimally, and they don't like those. And so some of those are what you see in those yellow cases of partially running. Often we classify them as running, but with, workarounds that we would like to get rid of. In other cases, the applications, projects had multiple applications. They started with one, they got that to the green state, and now they turn to the next one. And those are a lot of the orange ones where they're still, working on those ones to get them ready. But all in all, I think we've seen pretty good results in the application space. And so I want to walk through quickly just a handful of our applications and give you more concrete examples of what they are and what they're doing today and what they've been able to accomplish. So OpenMC is one of our codes. It's a Monte Carlo neutron transport code. It's used as part of the ECP XASMR project to model neutron transport and nuclear reactor simulations. So it's very computationally expensive. And this Monte Carlo neutron transport algorithm is really only practical on the latest generation of HPC systems. It just was too expensive to do before, but it is the highest fidelity way of doing these kind of simulations. And so it's something they really want to use, and now they're able to. The code is written in C++, and it uses OpenMP to offload to the Aurora GPU. It's been run across multiple GPUs. These guys have been working for years to get their code ready to run both on PVC, on the AMD GPUs, and on NVIDIA GPUs. So it's been well optimized across multiple GPU platforms. And this is one that we're seeing very good performance, performance that we're very happy with on the Intel PVC or Max GPU. So, as of today, what they're seeing, and you can see it in the bar charts in the upper right, is their performance on Sunspot, which is in blue. So this is a FOM, so higher is figure of merit, so higher is better, compared to their performance on an MI250 and an A100 platform. And you can see they're basically getting, better than a factor of 2, in many cases, better performance on the PVC GPU than they're seeing on the other platforms. In addition to that, there, the bottom right, we show some scaling results, and you can see they're scaling on the Aurora, Sunspot testbed compared to on other testbeds that use the MI250 and A100, and it looks very similar. And this is not unexpected because they're all GPU-based systems. They're all using a Slingshot network, and so this is kind of what we expect to see. And you'll see this in all of the applications have these sort of scaling results, and in most cases they look pretty familiar. Another application that we've been working with is the XGC application that is part of an ECP and an early science project. It's used for plasma physics simulations, and it uses the COCOS programming model. It uses different backends on different systems. So it uses SQL on the Intel GPUs, CUDA on the NVIDIA GPUs, and the HIP backend on the AMD GPUs. So the bar charts, you can see their performance, and again, higher is better for them. And again, blue is on Sunspot, green is on our Polaris system, which is an A100 based NVIDIA system, and yellow is on Frontier, which is an AMD MI250X system. And so again, we're seeing good performance, performance a little bit better than what we're seeing on other GPU platforms with this code, and we're seeing performance, scaling performance that looks very similar to what we're seeing on other machines. Another code that we've been working with and that's been running on our systems is the CRKA hack code. So hack is a cosmology code. It's used to simulate the formulation of large scale structures in the universe. It uses n-body methods and a novel formulation of smooth particle hydrodynamics. So this is a code that's written in C++, and it uses SYCL to offload on the Aurora GPU. So this is also code that's been well optimized by a very computationally strong team across multiple GPUs. So it's been set up to run on PVC, AMD, and NVIDIA GPUs. And again, you can see in the bar charts, the performance across these three platforms: the A100, MI250X, and the PVC. And where the blue being PVC using SYCL. And again, we're seeing performance that's comparable or better to what we're seeing on other platforms for this code. One of the interesting things is they've been able to use a feature of the PVC GPU that allows them to set up size the register file differently. And when they size it to the larger size, the 256 general register file size, they get better performance than they see at the lower scale. So this is a nice element of PVC that lets them tune the hardware to get the better performance for their application. I think I have two more applications that I'll just talk to quickly, and then I can take questions. This next application is NWChemX. It is a computational chemistry code. It is written in C++, and it uses multiple programming models, CUDA, HIP, and SYCL. The bar chart here in the middle is showing performance, and this is an interesting case because what they've done is they've compared both the performance using a native programming model, so that's HIP on AMD hardware, which is in the red. So the light red, or sort of pinkish bar, is their performance using HIP. And in this case, lower is better. So they did the opposite. They're just showing time here, time to solution. And then SYCL is the dark red bar, run on an MI250. So they're actually seeing slightly better performance using SYCL on an AMD GPU than they are seeing with HIP. And for NVIDIA, they compared SYCL, which is the dark green bar, to CUDA. So CUDA slightly outperforms SYCL, but really they're getting very, very similar performance with SYCL on AMD hardware to what they're seeing with CUDA. And then there's the performance using SYCL on the Intel Data Center Max GPU. And so that's the dark blue bar. And again, we're seeing performance that's on par or better than what we're seeing on other GPUs. And so the last application I wanted to mention, second to last application is QMCPAC. I won't talk about this. It's a quantum Monte Carlo code. In the interest of time, I won't talk about this in detail, but it's a C++ code using OpenMP, and you can see their performance being compared to the PVC, between the PVC, where higher is better, the A100 and the H100 from NVIDIA. And so again, I think performance is looking pretty good on the Intel hardware for this code. And the last code is NAMD, which is a molecular dynamics code. This is widely used in the molecular dynamics community. And it's a C++ code written using different backends, CUDA, HIP, and SYCL. And you can see their performance in the bars where higher is better. And they're getting performance that's on par or better than what they're seeing on other GPUs today. So all in all, we're very happy with where we are with the performance and the state of things. I mean, there's still work to do. This is sort of a never-ending process of getting applications, running, optimized, and then moving on to new applications. And we're certainly very interested in expanding the application base. Today we're working with about 45 applications, but that's really not. When we put the machine in production, we expect to see 100 to 200 applications ultimately using the machine over the years. So we still have quite a lot of work to do. And with that, I will take any questions. Let me see if there's
So to the moderators, if you could unmute yourselves.
Yeah, I actually have a question. Scott, thank you so much for the talk. In some of the results you showed was a single node performance. And then you showed some other application at the end, but I was not quite sure whether you were able to run on multiple nodes of PVC. Can you further comment on this? Yeah, I may have missed it.
Yeah, so if you look at all the application results we had, there's this scaling plot on the right side, and typically what they've done is plot on a number of how many GPUs they've looked at. So if you look at this QMCPAC one, right, it goes from 0 to 200, and that's the number of GPUs that they've used for their simulation. And in this case, they have the ideal scaling in the dotted red line. And so all of these applications, have provided some sort of scaling plot where they're running on, typically, on Sunspot today, we're not able to run up to 1,000 GPUs, but we're able to run up to a couple hundred. And so they've been able to run in all these cases. This one, they've run up to 512 GPUs on Sunspot and Crusher, which are PVC and AMD GPUs. So yeah, I mean, this is not nearly as larger scale runs as we will be doing ultimately. We'll be running on thousands, if not tens of thousands of GPUs. But it's a good start for the hardware we have today.
Thank you.
Were there any other questions? If not, I can just add a few final closing comments, which are that, this is, we've learned a lot from this process. I think it's, it's a change for the community. It's one that's been going on for years, but there are definitely challenges here. One is, the hardware continues to change and evolve. If you have a CPU code, one of the key things is, you have to express a lot of parallelism in order to take advantage of the GPU, and you have to be able to really get the bulk of your computation over onto the GPU. If you're constantly shuttling data back and forth between the CPU and the GPU, you lose a lot of time, there doing that kind of, back and forth. So it really is sort of, something where you have to get the bulk of your code over there. And one of the challenges today in the HPC space is in the programming model space, right? We have this diversity of programming models, which in ways is really nice, right? It's nice to have options, but it presents challenges, right? People are going to have to pick one of these ultimately to write their code in, and you really prefer to pick one that's going to be around 10 years from now, so you don't have to rewrite your code. And how that's going to evolve is a little unclear to me. I mean, I think things like OpenMP will be around. I don't know, with the proprietary, things like CUDA that are proprietary, historically those have not, stayed around over the long term, but it's hard to say what it's going to look like in the future. And one of the things we're trying to do from the Argonne side and the DOE is, take advantage of the work that AMD has done with HIP and make it, sort of more broadly available and more portable, so that you can use, something that is similar to CUDA to run across multiple platforms. So I think this is an interesting area for the community and for folks that are trying to understand how to get their applications ready for these machines. And the programming models question is certainly a major one.
So Scott, there are some other questions in the chat. The first one is, what are the plans for the PMEM feature in the system now? And then secondly, from that attendee, why do you use hot water?
Well, so the water side, we use, the water comes out hot. So the water goes in cold, it runs through the heat exchanger on the chip, and, we get hot water out. So we're not, but we are able to use relatively warm water. I think the water temperature going in is around 7, I'm not a facility, an infrastructure guy, but I want to say it's around 70 degrees or so, or it can be up to about 70 some odd degrees, but, and still be effective at cooling the system. So we don't have to get it really cold, which saves us a lot of energy. The PMEM part, I'm not sure I understand that question, so I might have to defer on that. But if anybody wants to contact me, my email is sparker@anl.gov, and I can try to follow up with things.
Scott, maybe another question. What are the remaining challenges to have Aurora up and running at full scale? Is this something that you can provide some insight on?
Yeah,
hardware or software or any aspect here?
So there's always a number of challenges with these machines, even once we have them. So the first one is shaking out all the hardware. So we literally have hundreds of thousands of components in these machines, and getting those all configured and making sure all the hardware is working. It takes a while. It's a process of weeding out the issues, resolving them, and incrementally making the machine run better at larger scale. So that's a challenge. I mean, we've done this before with other machines, so we know how to do it. It just takes time. I think the other challenge is really continuing to get the best performance out of the hardware. And so I think we are on a good track to do that at the node level. We haven't had a chance to do a lot of scaling. You know, we scaled up to a few hundred GPUs, but we really need to scale up to, you know, tens of thousands of GPUs. And so I expect we will see issues as we do that. And then, you know, making more applications work, right? So the programming models issue, you know, not all codes are written for GPUs today. A lot of those that are written in CUDA. CUDA runs great on NVIDIA hardware, but you know, if you want to run somewhere else, you have to figure out how to do that. And so whether people want to migrate to something like SYCL, which is more open and portable, or you know, look at something like HIP, which is sort of trying to address that concern for CUDA. So those are some of the challenges that remain.
Hey Scott, this is David Martin. I have a question for you. You were talking about building, you know, the application for ECP and ESP. Can you talk a little about, you know, the people who are on the call who are interested in running on Aurora at some point? What's kind of the timeline in the process to get access?
Well, so yeah, I mean, the ultimate goal is to have Aurora available to the broader scientific community. So, you know, folks who are interested in, you know, getting on the machine, you know, the first step is to prepare your application to run on a GPU, whether it's Intel or elsewhere, and preferably with a programming model that's portable. Like, you know, so if you write your code in OpenMP or SYCL, you can do that on any platform that you have access to that supports those programming models. And then, you know, that should let you run on Aurora. So also things like Cocos would work. You know, so that's an easy first step, is just get on any platform that has a GPU, take one of these programming models and get your code working there. If you've already done that, then the next step would probably be to get on, you know, an Intel GPU platform. And I know Intel has been rolling out dev cloud, you know, resources in their dev cloud to let people sort of, you know, get their feet wet with Intel GPU hardware. And I'm not sure the current status of that in terms of the resources that are there, but I think in general people can get on and at least run on the integrated GPUs, which is what we did very successfully, you know, back when we first started. So even though they're smaller GPUs, they are more than sufficient to, you know, give you proof of concept that your stuff works on Intel hardware. And the step from running on a smaller scale GPU to a larger scale GPU in the Intel ecosystem is not necessarily, you know, a major one in most cases. And so once we have that and people are able to scale, then, you know, it's really just a question of, you know, getting time on the machine, which is through the Insight allocation process.
Yeah, and just to clarify, that's open to anyone, both Insight and ALCC.
Yes, I mean, as long as it's, you know, open research, right? It's not for proprietary, but, you know, yes, for anybody in the scientific community that's looking to publish, that time is, you know, free on the machines if they get an award.
Thanks.
So, Scott, this is Amit from TAG. I just want to know, apart from the applications, are you working on profiling and debugging libraries apart from the Intel, like what they provide?
Yeah, we are working on a number of different libraries. So, you know, partly in partnership with ECP. So there's a lot of math libraries like PETSI, Hyper, Ginkgo. There's quite a bit of work going on to get those ready to run on, you know, Intel GPUs and other GPUs. In addition, we're also working with the broader set of community, you know, software, right? So there's, you know, you mentioned profiling. There's, you know, community tools like HPC Toolkit and Tau. They've also been working to, you know, get their software to run on Intel GPUs so that people can use it to do things like profiling, you know, PETSI or Tau or a full application. So yeah, we're really focused on the whole ecosystem, you know, that our users need to run successfully on the machines. And it's a process, you know, not everything's working perfectly today, but we are trying to make sure that everything's in the pipeline and should be hopefully ready for folks when they need it on Aurora.
Okay, thank you.